Hello everyone, and welcome to a new video from Machine Learning with Hamza. In today's video, we're going to try to answer an interesting question, which is, how can a CNN model identify and detect fake faces? So to do that, we're going to use a well-known technique in machine learning explainability. Machine learning explainability refers to extracting human understandable insights from any machine learning model so that we better understand what function this model learned when training and how does it process the input to produce a certain prediction. So the technique we're going to use is called Grad-CAM. Grad refers to gradients and CAM stands for class activation mapping. So this technique dates back to 2017, I believe. It is an improved version of the prior technique, which is called simply CAM. And this technique introduced the use of the gradients calculated from backpropagation to extract more information from the model and what it has learned, and to produce better results so that we can better visualize what the model is learning and how it is making the prediction. And to put it in simple words, what Grad-CAM tells us, or what it does, is basically tell us which part of an input image does the trained model focus on when predicting a certain class or producing any kind of prediction. So this is a very interesting technique and can be utilized in various tasks, like maybe diagnosing the model in order to increase its performance, or identifying biases towards certain classes in the dataset. And it actually can be used for any kind of computer vision tasks like classification or segmentation or visual question answering, or also image captioning. So it is very interesting. And today in this application, we're going to use it to answer the question we have in hand and to see how can a CNN model identify fake faces from real faces. It's actually a classification problem. So we're going to first train our model to classify images of fake and real faces. And then we're going to use the Grad-CAM to diagnose our model and to investigate it on how does it come to a certain prediction. And hopefully you find it interesting. So let's get right into it. So here we have a notebook that we're going to go through step by step. We're going to see how we pre-process the data, we train the model, but we're going to mainly focus on the Grad-CAM implementation using TensorFlow and Keras. And of course you can download this notebook from the link in the description. You can also find it in my profile on Kaggle, where you can run it on the Kaggle platform. And of course you have a Colab if you want to run it there. So without further ado, let's start with this notebook. So first of all, I'm going to see which libraries we're going to use. Here are the libraries that we're going to need in this notebook. So we have some basic libraries, OS, Random, GC, etc. We have Pandas, NumPy, OpenCV, Pillow, and Matplotlib, and some of the TensorFlow and Keras tools. Then of course we have the train test split from scikit-learn. You can ignore this second cell. I only use it in my local machine, so I'm able to train on my GPU. But if you're gonna run this notebook on Colab or on Kaggle, so feel free to comment it or even delete it if you want. Okay, so now let's move on to the data. The first one is a public dataset on Kaggle, which contains 140k real and fake face images. You can find it through this link here. So here we imported the datasets. We dropped some unuseful columns and then we flip the labels. So we need our real label to be 0 and our fake label to be 1. That's why we flip them. Then we separated the feature column from the target column. And then here I checked for class balance. So we have balanced representation of both classes in each of the train, validation, and test sets. Okay, so of course on my local machine I can't train over 140k images. It's gonna take forever. I only pick 20k and 3k for both the validation and test set. I checked again after picking a sample from the datasets. I checked for class balance again. Okay, so now I map each image to the correct path so we can access it later on when pre-processing. And here is an example of the images present in the first dataset we have. So here we have real images and some fake images. Obviously we have here hard images that even with the human eyes we can barely detect it. So here, for example, here we can maybe see that we have some issues with these parts of the image, but with the face it's all perfect. That is because it was produced using the style gun. Okay, so for the second dataset we're gonna use, this dataset we're gonna only use it for testing. I created it by collecting real images from Unsplash, which is a website for images, copyright-free images of course, and they provide an API to collect or to gather some images. And for the fake images I collected them from the This Person Does Not Exist website, which is a website for the Style Gun 2 images. Of course, images of people that doesn't exist. So we're gonna process this dataset the same way. We're gonna convert the labels to numeric, and we're gonna map each image ID to the correct path of the image, and here it is. So then we checked for class balance, and here is some examples of images from this dataset. And as we can see, the fake faces are very hard to detect, even for the human eyes. Okay, so for the pre-processing, we're gonna set the seeds first. We're gonna set some constant for the batch size, image size, channels, shuffle, the auto-tune. Okay, so these are the functions that we're using for the dataset pre-processing and creation. So we're gonna convert the pandas data frame, and we're gonna create TensorFlow datasets. To do that, we have this create ds function, which is going to take the X feature, which contains the paths to the images and the labels, where it's going to create a dataset from tensor slices. Then we're going to process this created dataset. So the process function is going to read the images using this function, which decode the JPEG images and resize and normalize them. Okay, so then after reading the images, as you can see here, the map read image function, that's going to read the images and decode them. If the dataset fed into this function is labeled as a trained dataset, we're gonna use data augmentation, and here it is. So we're gonna flip and change, adjust the contrast and the brightness, and use the crop function to crop the images, then resize them to the chosen image size. Okay, then after data augmentation, we're gonna shuffle the images in the dataset, and we're gonna use the batch method to divide it into batches. And then finally we're gonna use auto-tune. So here we have a batch size of 4, but this is of course for my local machine. On Kaggle you can use, I guess it runs perfectly with the batch size of 32, but of course on the GPU. Okay, then after creating these datasets for train, validation and test, and of course we're going to create the second dataset for testing. Okay, so for the model, here if you have of course the trained model, you can import it, but we're not going to do that here. With the pre-trained model we're going to use a ResNet 50 v2 with an input image size of 224. Of course we're not going to include the top. We're going to create our own top here, but we're going to freeze all the layers except the last conv layer of the ResNet, which happens to be at index -5. So we're going to freeze all the layers except the last convolutional layer. And of course the batch normalization layers are freezed also. So then we're gonna use the pre-trained model and add some dense layers on top of it with one output layer. So we use the sigmoid because we have a binary classification and we have a binary cross entropy here for the loss. So then we used an ADAM optimizer with the binary accuracy as the metric. So here is the training of the model. So here the results, we have the final accuracy over the train was about 97%, and the validation accuracy is about 85%. So here are the curves of the progress of the loss and accuracy. Of course, the aim was not to produce the best model we can, but to see how we can implement the Grad-CAM, and of course we're going to focus on that more later on. So evaluating the first test set, we have 82% accuracy, and the second test set, which is the second data set that we have 63% accuracy. And that is understandable because the first one was extracted from the first dataset, which was trained on, but the second dataset was completely different dataset. Okay, so now we're gonna calculate actually the confusion matrix to have a better idea on the performance of the model. Okay, here we extracted the true label and predicted labels on each batch of the test set. We concatenated them, and then we created a scikit-learn estimator from the TensorFlow model we have, so that we're able to use it here in the plot confusion matrix, because here it requires an estimator which is scikit-learn class. That's why we wrapped our TensorFlow model inside of an estimator, and there it is. We have the confusion matrix. So we can see here the precision and recall, and of course the F1 score. And I would say it's acceptable for this task. We're not focusing on the performance, as I said, but we're going to focus on the Grad-CAM algorithm and implementation and its results. So here we have the Grad-CAM algorithm illustrated in this image, which is from the original paper of Grad-CAM. So let's talk a little bit about this algorithm. Then we're going to see its implementation. So here we have an input image, and it is fed to a CNN. And then, for example, in our case, we have image classification. So the output of the CNN is given to fully connected layers, which present the head of the model. And finally, a certain class is predicted. The certain output is given here. We have tiger cat. So the model predicted that this image is of a cat. So the first step when performing Grad-CAM is performing forward propagation and producing a certain prediction. And based on the prediction we have, for example, here we have the label C. We're gonna backpropagate to a certain convolutional layer. For example, we have here this layer. So after backpropagating to this convolutional layer, we perform global average pooling, which produce this vector of weight importance, and then we multiply it by the class activation mapping of this convolutional layer, and the result is then passed to a ReLU function, which produces a heat map as an output. The heat map is then processed and resized to match the size of the input image, and then we can overlay it over this image to better visualize the result of the Grad-CAM. So this is basically the algorithm of the Grad-CAM and how it works, and we're going to see now how to implement that using TensorFlow and Keras. So first of all, we're going to need the Keras backend. I'm going to create the Grad-CAM function. Okay, so we need a model which takes the input and produces the output of the chosen convolutional layer by its name. We're gonna access it by its name here, and of course the output of the model. And here we're gonna have the predicted class. So this is a clone model created using the trained model we have. Once we have the grad model here, we're gonna use the gradient tape to backpropagate until the convolutional layer we have. So here we have the inputs. We pass it to the grad model we have, and we get the outputs, which, as we defined here, two outputs. The output of the convolutional layer, which is the conv outputs, and the predictions. And then, of course, we take the argmax of the prediction, so we can have the class ID. But of course, in this example, we have only one class, so it's gonna be redundant to use it here. But this is very important if we have more than one class. Okay, so now using the ID, we get the losses. And using the tape gradient, we backpropagate the loss of the predicted class until we reach the convolutional layer we picked, and then we extract, of course, the class activation mappings and the grads. Then we perform global average pooling using the reduced mean over the grads that we calculated, as shown in this image or in this step. So after backpropagating, we perform global average pooling. So after performing global average pooling, we calculate the linear combination, which is basically a dot product, and then we sum over the component of the vector. So we multiply the weights by the conv outputs, which represent the class activation mapping, and thus we have the Grad-CAM. But of course, we have to pass it as a final step through a ReLU function, which is made here after some steps of processing, which are basically normalization, min-max normalization of the produced Grad-CAM. And after performing the ReLU function, and of course the resizing to match the input image size, we produce the heat map, and this concludes the function of Grad-CAM. So using this function, we can feed a model, an input image, and a layer name as an input, and as an output we get the Grad-CAM and the heat map, which we can use in this function superimpose to superimpose the heat map over the input image, or to make it more understandable visually. Okay, so now we need to talk about the second part of this image. So this second part of the illustration describes how we can produce guided Grad-CAM, which is basically a combination of the Grad-CAM heat map talked about earlier, and the guided backpropagation. So guided backpropagation is very simple and very easy to produce. So guided backpropagation is basically backpropagating from the output until the input layer. This guided term refers to using guided ReLU function instead of normal ReLU function while backpropagating, and that is to negate the effect of negative gradients, and we only need to capture the effect of positive gradients, because the positive gradients have the effect over activating the predicted class, and that's what we want to capture. So we want to capture which gradients have produced this result, or which gradients are responsible for producing this result. So any other gradients, either null or negative, we're not gonna account for, and this is why we use guided ReLU. So now let's see how we can implement guided backpropagation and guided Grad-CAM. So first of all, we need a guided ReLU function. It is defined here using this decorator, so we can use it in backpropagation. Then we defined the guided backpropagation function, which takes the model and the input image as inputs. Then we cloned the guided backpropagation model from the trained model we have, and we replaced each ReLU function with the guided ReLU function defined earlier. So for each layer in the model that has ReLU activation, we change that layer activation with the guided ReLU, and then we backpropagate normally from the outputs to the inputs, and by normalizing and by stacking the produced grads and normalizing the produced image, we can capture the guided grads. So the guided grads here are present in this illustration as this figure. Finally, as a final step, we can multiply both the Grad-CAM heat map by the guided backpropagation to obtain the guided Grad-CAM, which is done in this function, guided Grad-CAM function. It takes the guided grads and the heat map and it multiplies them to produce the guided Grad-CAM. Finally, we need this deprocess image, which can be found in the Keras GitHub under the conf filter visualization .py file. So what it does, it basically normalizes the tensor, clip it to 0, 1, and then convert it to RGB. Okay, so now let's see some results using these functions. So I created this print results function, which takes index x and y and the model to produce the Grad-CAM for every convolutional layer, the guided Grad-CAM for the last layer, and as we can see here, let's see some results. For example, for the index 38 of the train set, and using the trained model, we can see here the results of the Grad-CAM, guided backpropagation, and also the guided Grad-CAM. So here the input image was predicted as fake, and it is indeed fake image for human face. So here in the final layer Grad-CAM, we can see which part of the image the model focused on when producing the result. So here it focused on this part of the human face, which is not really understandable on this image why exactly it is that, because even with the human eyes we can't see what's really wrong with this image. Here with the guided backprop we can see which parts of the image activated the neurons the most, and using the combination of both of these we can see which parts are more important to the model to produce the fake prediction you can see here. So this is only an example of one image, but let's see an example of maybe 10 images. So this function generates an unsample results. So here it takes X and Y for inputs, the model, and the target label. So here we have the fake label, and we're gonna produce 10 results taken randomly from the X train and Y train sets. So here we can see that the first image is predicted fake, and it is fake, and we can see which part of the image was focused on by the model. We can see the Grad-CAM also for each convolutional layer, and for example here we can remark that this layer always focuses on the eyes region. Even for example, for this image we have the same remark, of course, for this image and for this image. So the model, we can see each layer of the model, which part of the face or of the image the model focuses on. For example, for this layer, the model always focuses on the background and ignores the face. So let's see, for example, here. As you can see, it ignores the face and focuses on what's around it. Of course, here also, and here also it focuses on. But what's important is the last layer, because the last layer is responsible for the prediction that the model gives. So we need, in order to understand, we need to focus on and to investigate the last layer Grad-CAM. And of course, to diagnose the model and to better investigate it, we need to pick certain images that present certain challenges and certain aspects that we can feed them to the model, see the Grad-CAM results, and then based on those results we can extract insights and draw conclusions on how to increase the model performance, or whether the model is biased towards a certain type of images. For example, here we can feed a batch of images of faces from certain ethnicities, and we can see if the model is biased towards one of them or not. And with that we came to the end of this notebook. Of course, you can have more fun with this model and this implementation of the Grad-CAM on Kaggle or Colab using this notebook, and you can find more results, interpretation and investigation on the blog post I made on this topic. You can find the link in the description. Here is the blog. So how does neural network detect fake faces? You can see here for the results. You'll find a more thorough investigation with certain images that I picked especially to investigate the problems with this model, and of course to draw useful conclusions. So with that we came to the end of this video. I hope you find it interesting, and I hope that you learned something new, or maybe you better understand the Grad-CAM and how it works and how to implement it on TensorFlow. So thanks for watching, and until next video, stay safe.